All right, so welcome everyone. Uh, this is MSU St. Andrews Astronomy Night. I'm Dr. Edmund Stark at the MSU STEM Center, and our topic is how the universe was discovered in the constellations of fall. So this is going to be a mixture of astronomy and history and a little bit of arts because there's actually going to be some mythology involved in this. So maybe it's the STEAM Center instead of the STEM Center. The agenda is what's out in the sky tonight and this month, planets, where they are, seasonal patterns, fall constellations, and meteor showers, like one of our alert observers, one of our alert guests asked. Our focus tonight is the discovery of the universe in the constellations of fall in particular. So I'm only going to be talking about things that happen in the sky right now. And I'll be talking about the Perseus legend and the main characters, Perseus, the Gorgon, Cassiopeia, Cetus, Cepheus, Andromeda, Pegasus. These are all characters in the legend, and each of them have something very special associated with them. And I'm going to end with a few words on the Arecibo telescope. So I'll start off with maybe the most important event that's going on right now, the winter solstice. It controls our lives. It controls our crops. It controls our agricultural cycles, our temperatures. Throughout the fall, you've probably noticed the sun has been rising further and further south, peaking lower and setting further and further south. So we get very little daylight. This has been going on all fall, and the sun is moving south and south, but it's starting to slow down. And on the winter solstice, that movement all stops. The solstice is Latin for sol and sistere, for the sun to stand still. The sun sets the furthest south and is the lowest at noon on December 31st. So it's the shortest day and the longest night of the year. After December 31st, everything reverses and the sun starts getting higher in the sky again. And to illustrate what this looks like, I'm going to show you this figure on the right, which is an almanac that I personally use for putting these talks together. Without worrying about what all the lines on it mean, let's just look at the general shape. It's the length of the night. And down here, oh, I don't have my pointer yet. Where is my pointer? There we go. So this is the length of the night. You can see here, this is January through June through December. So the months are up here. Nights are very short in June, about 9 hours, where nights are very long in the winter, almost 15 hours. And we are right here at pretty close to the longest time of the year. And technically, since this is 2021, we're actually up here in December of 2020. Let's talk about where the planets are. I update this every presentation. Here's the Earth, that green disk. And here is Venus. It's on the far side of the sun right now and moving behind it. It's past its peak brilliance, but it's always the brightest thing in the sky other than the sun and the moon. Mercury in its orbit here is nearly behind the sun. It will actually pass behind the sun on December 20th, which is called a superior conjunction. So we're not seeing it. Mars was recently on the other side of the Earth, a beautiful opposition on October 13th. It is moving, we are moving away from it, to be more precise, but it's still the best view of Mars for another 2 years. Jupiter, you see this horizontal line near the bottom here, the quadrature line. Jupiter just passed eastern quadrature. It's about here, and we're moving rapidly away from it. And Saturn is way up here. It also passed quadrature fairly recently. And they look like they're kind of lined up. And in fact, they are. And that's the first, or I should say, the next thing we're going to talk about, the Great Conjunction. Great Conjunction literally is a conjunction of Jupiter and Saturn. That's what that term means. Jupiter is the brightest thing in the western sky at night. It'll be very close to the setting sun. Saturn is just a little bit above it, and we can see the two of them here. They're very close. They've been getting closer to each other in our point of view for years, and on December 21st, it finally happens. Jupiter will pass right by Saturn. This only happens once every 20 years. And this year is very special. It's the closest they'll come since the year 1623, 400 years ago. And they'll be only about 1/10 of a degree apart. Don't miss it. And don't worry about the 21st if it's because it might be cloudy. If it's the 19th or the 18th and you see a clear sky, go out, look to the west and see those two together. You'll be rewarded with something very special. As far as the rest of the night, Mars dominates the night once Jupiter and Saturn have set. It's the brightest star after dusk. Easy to see. Look at the finder chart. There's one thing in it, Mars. Right here, you look to the south and you'll see it. Interestingly, Mars has, the planets all generally move west to east against the stars. But in September, that motion stopped. It's called a stationary point, and Mars began to move backwards, went through opposition, but then it hit a stationary point again, and it's now moving forwards again. Earth is moving away from Mars right now, as I showed in that diagram earlier. So Mars is getting smaller and fainter. So if you want to see it, if you have a telescope, now's the time. And here I've prepared a little movie. This is a little different from some of the ones you've seen before. This bright thing here is the sun. So it's daytime, but I've pretended like the sun was not there so that we can see the constellations. And I want you to pay particular attention to this thing I'm circling, which is the planet Jupiter, and this thing I'm circling, which is the planet Mars. This starts in about February, so maybe 10 months ago. And I'm going to roll this clip, and I want you to watch them move as they get moving. There they go. They're both moving in prograde, and now they both stop and go into station. They move backwards and get further apart because Jupiter moves faster than Saturn. Now they're in station again together, and Jupiter passes by. Right now, that's what's going to happen on the 21st. And basically, from then on, Jupiter is going to continue to move further and further from Saturn until they make their way all the way around in the sky. I want to show that to you again. And this time I want you to pay attention to this star in Ophiuchus, not a zodiacal constellation. This is Mars. And watch what Mars does once we get going. It'll move pretty much blows right past Jupiter and Saturn, and off it goes. And you can see it moving across, but it's getting brighter. Can you see that? It's getting brighter and redder. And now it goes into station at Pisces. That's September. Now November, it returns back to prograde and is gone. So that's the kind of thing that astronomers get to look at. And you can see that yourself with your own eyes if you just pay attention to the planets. Now I want to look at the pre-dawn sky. The brightest star in the sky is Venus. It's in the mornings. It's getting closer to sunrise because, as I said earlier, it's drifting backwards into the sun. And it's approaching the far side of the sun next March. Mercury is too close to the sun to see, but when will we see it? Mid-January, basically. So here is Mercury. On January 14th, you have an opportunity to use the early, if you can see the crescent moon on January 14th, Mercury will be slightly below it. But Mercury will continue to rise, and by late January, it will be a little bit better positioned to be able to see. But it's usually a good idea to grab a pair of binoculars. And you notice our friend Fomalhaut, which is a star I've mentioned in the south, by January will be heading into the sunset and will be going away. Now, meteor showers. There are two good meteor showers coming up, Geminids and the Quadrantids. The Geminids, frankly, if you're not worried about temperature, because Perseids in the summer are warm, Geminids are the best of the year. They can have a meteor a minute, which is a shower. That's a pretty good meteorite. It peaks on the evening of January 13th. And what's nice is that the area, this is called the Geminids because it radiates from Gemini. The meteors come shooting out like this. And this is high in the sky by 9 at night. And there's no moon. I should say there's a new moon that night. So the brightness of the moon won't mess the sky up. Perfect time to view the Geminids. View them on the 13th or maybe a night or two before or after. Geminids have a fairly narrow peak. The Quadrantids are all, they're named for a constellation that no longer exists. That might be a subject for a later talk. But before dawn, so not 9 p.m., but like 4 in the morning on January 3rd, They radiate here, so they'll be perfectly fine. You'll be able to see them all night. But the waning the waning gibbous moon will be fairly bright and will interfere. You won't see the faintest meteors. So two good opportunities. So I've just taken out these first few bullets here and the meteor showers, and I have all this other stuff yet to cover, but I thought this would be a good time to stop if there are any questions.
We don't have any specifically on the talk itself yet, but there's one. What are some of the largest known stars?
Oh, there's all kinds of stars that are really big. I'm a little bit behind in this. I mean, there's one called S Doradus, which is absolutely humongous. But a few years ago, people discovered that it was actually a multiple star. I think there's a VY Canis Majoris is a very large star. These are stars that are about 100 times the mass of the sun. There are theoretical limits, which I'm not really readily able to go into. Well, I might not be qualified to go into, which make it hard for a star to actually be larger than that. So as we understand star formation, that's about the limit.
Okay. We have a question about the Geminids. This person believes they peak on December 13th, not January 13th.
Oh, did I put January? Oh, thank you very much. Oh my goodness. Yes, that is a mistake. They peak on December 13th. Thank you very much. I will have to fix that slide. Oh my goodness. Yeah, that's a nightmare.
Well, good error catch. Okay, we starting to get a few more questions pouring in. Once Venus goes behind the sun, how long until we see it at night again?
It'll be a couple of months. Venus is very bright, but because it's moving to the left and we are moving to the right, so to speak, we're kind of moving around past each other, and so the sun is in the way for a long time. If you're out there with binoculars, you could be able to see it, but from when it's really like up there in the sky in the morning to when it's really nice in the sky, easily seen, it'll be a couple of months.
Okay, and here's a nice relevant topic. What's the best method for looking at meteor showers? Just sit outside or take binoculars?
You don't need binoculars because binoculars look at a small part of the sky and meteors are shooting all over. The best thing is to find wherever the radiant happens to be and to just sit down so you're looking more or less square at it. So if the radiant happens to be fairly high up, like it can be for the Geminids later at night, you might actually want to bring something in like a chase lounge and lie on your back. But yeah, you don't want equipment. You just want your eyes, and you want the equipment you need is a dark sky. You always want a dark sky, and that way you'll see the fainter ones as well as the brighter ones.
Okay, and I'd say we have about two more questions that are really relevant.
All right.
What would you consider to be the best time to see meteor showers?
It's when they're active. So there are showers that occur at regular points during the year, and the Geminids right now in December, not in January, in December are a really good meteor shower, and the Perseids in the summer, in August, are good times to see meteors. There are other showers that have their quirks, like maybe a higher portion of big meteors, but those are probably the two best.
Okay, and how come you can only see planets sometimes?
Well, planets are in the sky just like the sun is. And for example, if the planets are near or anywhere near the sun, they're in the sky during the day, so you can't see them. That's for the most part. When planets are in the sky at night, they're perfectly obvious. So
Okay.
it would just be clouds. So
Okay.
we move on.
I'd say one last question, and then I'll let you move on. During the Perseids, when this person looked up, they noticed the sky flashing like there was lightning, but didn't see an actual meteor. Is that common? They weren't sure where the flash was coming from.
I don't know what that is.
Okay.
I'm wondering if it might be like a flashing spotlight, strobe light somewhere. I don't know. I did not notice that at the night I was looking at the Perseids. All right. So we'll start moving into tonight's focus because I'm going to talk about finding constellations when we're talking about the actual constellations. So I'm going to start with the legend of Perseus. It begins with a man named Acrisius, who was a king in Greece, and he had a problem because he had no male heir to pass his throne on to. So he consulted some wise people, and they told him, to his dismay, that he will one day actually be killed by a son of his daughter, whose name was Danae. He didn't want to kill his daughter, so to prevent this from happening, he simply imprisoned Danae in a tower. Nonetheless, she was given a son through Zeus, the king of the gods, and this bothered Acrisius even more, so he simply put the two of them in the chest and set them afloat in the sea. And here's a nice picture of that. Now, Perseus is in red, bold. Whenever you see something red and bold, it's been placed in the sky by the gods. So that's Perseus is in the sky. The chest floats to an island called Seriphos, and they're brought to the king Polydectes. Perseus eventually wants to marry Danae, or sorry, Polydectes wants to marry Danae, but her son Perseus doesn't want to allow it. So Perseus comes up with a plan to get Polydectes, comes up with a plan to get rid of Perseus. He asks his guests to a wedding to bring a gift, and he wants specifically a horse. Perseus doesn't have one, but he's very arrogant, and he says to Polydectes, "You name the gift." And Polydectes asks Perseus to bring him the head of a gorgon. So you see this is in red, there's a head of a gorgon in the sky. So what's a gorgon? Here's a gorgon. Take a look at this pot. The word basically means grim or dreadful, gorgon in Greek. Monstrous women with brass claws and teeth of pigs. The main thing is this hair here, which is actually snakes, and they can turn you to stone by looking at you. There are 3 of these. 2 of them are immortal, which means they can't be killed. One, Medusa, is mortal, and so she becomes Perseus's target. He is outfitted by some well-meaning ladies, and he receives a leather knapsack for the Gorgon's head, a very strong harpy, a kind of a sword, a helm of darkness, which makes him invisible, winged sandals, you can see him putting these on, which allow him to fly, and a very polished shield. This is almost like reading a Dungeons and Dragons book. He meets the Gorgon, he flies to the cave, and he finds Medusa asleep. But he's clever. He does not look directly at her, but approaches her by looking at her reflection in his shield, and he cuts off her head. From her blood springs Pegasus, the winged horse, who is in the sky, and he escapes from the sisters with his helm of darkness and his fancy shoes, and he begins his return journey. He comes to the ends of the earth, and he finds the Titan Atlas. He asks for hospitality, but is refused because of a prophecy, which actually involved someone else. And Perseus is indignant and takes out the Gorgon's head, and Atlas sees it and is turned to stone. And if there's any who doubt this story, Atlas was a great giant, and the Atlas Mountains in Northwest Africa are said to be what Atlas became when he was turned into stone. And actually, the Atlantic Ocean is the ocean of Atlas. So interesting. But continuing this poem, here's now where we start hitting the jackpot. He sees a woman chained to a rock at the seashore. He is in Ethiopia, and that is ruled at this time by a king named Cepheus and a queen named Cassiopeia, who are in the sky. Their daughter Andromeda is very beautiful, and the queen boasted she was more beautiful than Poseidon's sea nymphs, which makes Poseidon angry. And he floods the land so that he has control over it and sends a sea monster to ravage the land. And an oracle tells them the only way to fix this little problem is to sacrifice Andromeda to Cetus, the monster. So they chain her to a rock by the sea. Well, Perseus comes to the rescue. He flies down with his sandals and his stuff, and he destroys the monster. And you can see his sandals here, and his shield and his helm. And I chose this picture out of the trillion that are on the internet because he actually has a harpy here. This is what a harpy looks like. It's not quite a sword. And he kills Cetus, the sea monster, weds Andromeda, and there's all kinds of other things that I'm going to skip. This is a famous story. It has many variations. If you know the story, you may have heard that Perseus flies away on Pegasus, the winged horse. The winged sandals apparently are forgotten in that version. This version I found on the internet, and I was wondering if it really was Perseus at all, because he seems to be, I mean, he's got his helmet and his sandals and he has the bag with the Gorgon's head, but he's actually throwing rocks at the sea monster. You know it's Perseus though, because the names are actually written right on the amphora. So it's another version of the Perseus legend that I don't even know. Perseus returns to Sardophos, and the king doesn't believe that he actually got the Gorgon's head. He demands to see it, like a knucklehead. You can guess what happened to him. And there are other adventures, but to summarize the legend, Perseus is tasked with killing a Gorgon. He cuts off the head of Medusa using her reflection in his shield. From her blood springs Pegasus. On his return, he sees Princess Andromeda, daughter of Cepheus and Cassiopeia, and he kills the sea monster Cetus, who is threatening her. So these mythical figures have been placed in the sky. Here's a silly question for you. What is the sky to an ancient Greek? The sky was a sphere, a solid dome that surrounded the earth. The stars are fixed onto it like little jewels, and it rotated around the earth. A solid sphere, the stars are fixed, unchanging, eternal, and perfect. This is the realm of the heavens. Now, the planets don't quite fit into that because they move relative to the stars, so they have their own spheres. The Greeks had that figured out. How was the legend placed in the sky then? They were all placed in the sky as constellations. So I have to ask, what's a constellation? It is a group of stars that forms a pattern in the sky. That pattern depends completely on culture. Other cultures have different groupings than Western culture. Ptolemy the Great, whose picture I have here, had 48 constellations in his Almagest. Almost all are still in use today. Modern astronomers have 88 constellations, including some in the southern hemisphere that we can't see. So, examples of a constellation. The Big Dipper, America's favorite constellation. The problem is the Big Dipper is not a constellation, it's an asterism. You have to ask, what's an asterism? Any pattern that's not a constellation. It can exist within or across constellations. For example, here is the Big Dipper, which most of you will recognize, but you can see that it is part of a much larger constellation with paws and everything called Ursa Major, the Great Bear. You may remember we've talked often about the Summer Triangle, okay? The Summer Triangle is an asterism that spans 5 constellations, so it's bigger than a constellation. And the meaning of these patterns depends on the culture. Now, we all know this as the Big Dipper, but my father, growing up as a German in Hungary, knew this as the wagon. You can see a wagon on the side here, the heavenly wagon, the Himmelswagen, and here's where you hitch up your horses. Going the other way, you can see this in Britain and Ireland as the blade of a plow, and here is the handle of a plow being pulled by some horses out here. So all different cultures for the same group of stars. But the very appearance of these stars as a pattern, remember, there is no heavenly sphere. Some stars are close, some stars are far. They simply are in that pattern by chance based on our perspective. And how can I show you that, our perspective? I'll show you this video, if I can get it started, which pulls the sun away from the Big Dipper and moves around it. And you can see how the pattern changes as we travel around. But when we come back to our current point of view, we again see what we know as the Big Dipper. So it all just depends on our perspective. The further we are off to the side, we can, oh, what is this? Let's get rid of that. All right, so let's move on. So how do we find all this legend in the sky? By doing something called sky hopping. This is how you recognize constellations, and it all starts with the Great Square of Pegasus. That's an asterism within the constellation of Pegasus. It has 4 nice, bright second magnitude stars. This is important. This is a key landmark in the sky that's important to learn for anyone who wants to become familiar with the sky. It's like the Summer Triangle, It's like Orion in winter, or the winter hexagon, which is also useful. And it's like the Big Dipper, which is not easy to see in the sky right now. You learn these landmarks and you'll never get lost in the sky. So now, how do constellations keep us from getting lost? Well, remember, the Big Dipper is bright and easy to find. All right. Has six, well, that went a little too fast, has six bright second magnitude stars. This one's a little fainter. And it's easy to find because it is always in the northern sky. It's very close to the north. The furthest stars, these two here, are very useful because they, as is written right here in this chart, point the way to the poles. Stop that. Point the way to the pole star right here. Finding this star lets you know which way north is, and you'll never lose direction, even if you don't have a compass or a GPS. Now, can Pegasus do something like this? Even better. Here is, I have as information, if you wish me to email it to you, some star charts that I use. And here's one. Here's how to use it. You grab it and you look to the south. So you put the south right at the bottom. And up at the sky, this is the zenith, the point directly overhead. So you can see here is Pegasus, and it is fairly high. I'm going to help you find Pegasus, and I'm going to cheat, because right now we have Mars in a very good location to find Pegasus. A month or two from now, this won't work anymore because Mars will be gone. But by that time, you'll know Pegasus. So here is Mars. And if you just look a little bit to the northwest, or sorry, if you look a little bit up and to the right, you will see a big square of 4 bright stars. Nothing else comes close. You can't miss it, as the great square of Pegasus. All right. Now, how do we use it to find other things? Well, we use this as pointers. For example, the back stars point, as we see it, to this star here called Fomalhaut, which I've often mentioned because it's a very southern star, which you can easily see. Now, that makes it interesting because you never know what you're going to find on the internet. Here's a star chart, some of the ones I look at, and it has Fomalhaut in a ridiculous position. It is nowhere near there. And I don't know how these things happen, but 1 out of every 50 things I pull up on the internet is wrong. So if you're doing research for school, pay attention. You got to know a little bit about your subject because there's a lot of silly stuff out there. But anyway, getting back to where we were, here's south, and here's the zenith, and there's the great square of Pegasus right here. Now, Pegasus is a horse, a winged horse. I don't see any wings, okay, but look at this. Here's a body, here is a long neck, and here's the nose of the horse. The horse is upside down, and even, I won't talk about M15, a little cloudy thing like the breath of the horse. It has 2 legs in front. It has 2 legs in the back. It's at full gallop. This is obviously a horse. I imagine many cultures thought of this as a horse. This is about as good as it gets for a constellation. Here you'll notice the word Andromeda between the horse's hind legs. It turns out that the constellation of Andromeda is what amounts to the hind legs of the horse. And we'll talk about that more often, but this is not technically part of Pegasus. It is the constellation of Andromeda. So finding the great square of Pegasus immediately allows you to find Andromeda. Using the pointer stars on the bottom of Pegasus, if you take this distance and go once, twice, a little bit more, you will find this star called Menkar. And using the other pointers, once, twice, and a little bit more, you will find the other bright star in the constellation of Cetus called Difta. There's not much in Cetus. There are 2 bright second magnitude stars. Everything is dim, but they're both easily findable using Pegasus's pointers. And what's interesting in Cetus is this star called Mira. And if you see up here where I've got the zenith, I'm going to move that circle over to this M31. This is the thing that's going to be interesting for us in Andromeda. And we'll talk about that when we come to Andromeda. But for now, a little bit more sky hopping. Before we were facing south, now we are facing north. And here's the point directly overhead. So you notice Andromeda is pretty much directly overhead. I'm going to help you find the other stars. You may remember the summer triangle, Vega, Deneb, and Altair. Vega is the brightest of the 3. I'm going to make it even easier. Look to the north and look at the 2 brightest stars, Vega and Capella. Nothing else is as bright as those two by a factor of 2. Draw a line between them, and that line passes right through Cepheus, which is fairly faint. Cassiopeia will be this bright cluster of stars above it, and Perseus is over here. And another way of doing this is, notice the Big Dipper is very close to the horizon. So it's always in the sky to some extent, but if you have trees, you're not going to see it. But if you can find the Big Dipper and you remember those pointer stars that point to Polaris, those pointer stars, if you allow them to go past Polaris, will get you to Cepheus as well. And I'm even going to give you another way. Here's north. Here's the point overhead. And remember the great square of Pegasus up there? Way up here, it'll be over your head. You'll have to crane your neck back to see it. But take that corner star nearest to zenith, Alpheratz, and go boom. Mirak, boom. Almach, boom. Mirfak. 4 bright second magnitude stars. Oh, and I should be clear. First magnitude are maybe the 20 brightest stars in the sky. You can only see about like 7 or 8 of them at a time. Second magnitude, you're not the brightest, but you're in the top 100. Okay, so these are bright stars. 4 bright stars along the backbone here of Andromeda, and they take you right to Mirfak in Perseus. So here's the constellation of Perseus, and we are interested in this star right here, Algol. And to the side of Perseus is Cassiopeia, bright, and beyond that is Cepheus, more dim. All right. And what's interesting in Cepheus is this little star called Delta Cephei. So we've got our constellations located. I've talked about the Perseus legend and how to find them. Quick break for questions.
Sure. Here's a fairly quick one. Will MSU do this often? I assume astronomy night.
Yes, MSU will do astronomy night roughly once a month. I'm sorry, I've been lax. I don't know when we're going to be doing this in January, but we try to do it once a month. The only time we don't do it is in the summer months because we have interns, and we only do 1 or 2 in the summer instead of 3, because that happens to be the busiest time for me and for the entire staff. So there should be 1 every month. And as time goes on, we may be able to start doing these non-virtually again, in which case, if it's clear, we will actually have observing afterwards. We have a nice collection of telescopes, but that hasn't been an option for almost a year now, since March, because of COVID.
All right. Are there any apps you would recommend for stargazing?
Well, I am old enough that I'm not a app recommender. There's so many. I would love to use my phone more, and there are in fact apps that apparently show you the sky fairly easily. With I've not used them. I prefer star charts. I don't know if I want to get too much into my own personal beliefs here, but if you actually read the terms on most apps, you are allowing that app. I mean, the app is not free. You're giving the app information. And so it will read your email, check your schedule. I find it kind of an invasion of privacy. So I normally don't hook up onto an app unless I need it for work. So I'm a minimalist when it comes to apps. There are fine apps out there if you're willing to give up the privacy. But what they are, I can't say.
Okay. Do all stars in the Milky Way have names?
No. There are so many stars in the Milky Way. The stars are named, if you've caught the names that have been given you, most of the stars that we use have Arabic names because of the great Arabic astronomy traditions in the 900s, 1000s, 1200s. They also have Greek names, and many of them have Flamsteed designations and things like that. And when it comes down to it, they will typically name a star by its coordinates. So many degrees right ascension, so many hours and minutes right ascension, and so many degrees in declination. And that will be the name of the star that's at that position.
Okay. What's a good resource to find out when all the meteor showers happen in North America?
A good resource for, well, the meteor showers will happen worldwide. It just depends what part of the planet is facing the sun or not. And I would recommend going to the, oh, what are they called? Not the variable stars. There's a American Meteor Society. I think that's the right name. And I usually get my information from them, but I get my illustrations from Sky and Telescope or from Earth Sky.
Okay.
Yeah, I don't come up with most of these drawings. I pull them off the internet.
Okay.
And there are often mistakes. Until about 2 hours ago, I just happened to notice that the image that I had for the Geminid meteor shower had Jupiter in it. The website put up the wrong year's image. There's no Jupiter in the sky when you're looking at these. So these things happen. Fortunately, I caught that one. I did not catch that they were in December and not January. Thank you for whoever pointed that out.
Okay, I'm gonna lump these two questions together. Is there a specific time of year better for stargazing? And is there any time when constellations are particularly bright?
Um, Timing depends on what you like. In the winter, nights are long, which means you go out at 6 and it's dusk, and you go out at 7:30 and it's dark. You can stargaze at 7:30 at night, 8 o'clock at night, no problem. But it's cold. Summer is nice and warm, but you know what? You have to wait sometimes until 11:30 at night before it's dark. That can be annoying for a family with young children. As far as when there are bright stars, I would have to say a couple months from now, um, Vega and Deneb are nearly circumpolar. They'll still be in the sky in January, but Orion will rise. Orion's already in the sky right now, and Procyon and Orion's got lots of first magnitude stars. Canis Minor's got a lot of bright stars. That section of the sky by the winter hexagon, I think, has the brightest collection of first magnitude stars than any time in the year. And that will be coming in a couple of months. Or if you simply wait a few hours, they will drift into view as the Earth turns, but it'll be later at night.
How about one last question, then we can move on?
All right.
What other legends are in the sky?
Well, most of Ptolemy's constellations have a legend associated with it. The more modern ones, like the ones that Hevelius put in, or Bayer's constellations, and those are more to fill up space. But I'll just give you one more example. The example, since I've already mentioned it, of Orion the Hunter, a man who boasted he could basically hunt anything, and he was the master of all. So Zeus sent a scorpion into the sky. Sorry, sent a scorpion after him, and Orion was killed by a scorpion. The great hunter killed by this little 3-inch thing crawling on the ground. And to remind everybody of Orion's lesson, both Orion and the scorpion were put in the sky, but Orion was put high in the winter sky, and the scorpion as Scorpius. And incidentally, Scorpius is one of those constellations. Anyone would look at Scorpius and would recognize a scorpion. It is clear. And Scorpius is in the summer low in the sky. So they are never in the sky together at the same time because they are enemies. So just one more legend. The sky is rich with these. But I would say none as populous as the one we're looking at. All right, so time to move on.
Yep, I would say so.
So now we're going to start looking at the individual constellations and what makes them all special. Okay, so I said the mythical figures were placed in the sky. You remember this figure, right? The solid sphere, stars are fixed, unchanging, etc. Turns out that's not true. And what's cool is that even the ancient astronomers knew it. And how did they know it? Because of something in Perseus. So I told you Perseus and the Gorgon's head are in the sky. Here's Perseus. It's a kind of a close-up. It's an average size constellation. But the interesting thing is this right here, Algol, the demon star. It's an interesting name. That AL in front, or the EL in front, is always a sign that it's an Arabic star. So the head of a ghoul. In Hebrew, Rosh Hasatan, the head of Satan. Why would everyone call this star such a nasty name? Because every now and then it dims by a factor of 3 for a few hours and then comes back up and acts as if nothing happened. Normally, it's almost as bright as Mirfak, this nice second magnitude star here, but then it drops so that it's less bright than any of these bright dots along the main arc of Perseus. This must have annoyed the ancients to no end. Now, who discovered this? Well, the names imply that this was known in antiquity. Every culture has a foul name for this star. But the first definite note is Geminiano Montanari, who made the first recorded observations of the variability in 1667. And it wasn't for another 100 years that a man named John Goodricke discovered the periodicity of algol. Periodicity, it has a period, it repeats. The decreases in brightness are not random. Algol dips every 2 days, 20 hours, and 49 minutes. And the dip is really short, only about 6 hours. Few clouds, you're going to miss it. So John Goodricke, very interesting character, deaf and mute since childhood. And it requires a lot of patience to do this because, like I said, a few cloudy hours and the chance is missed. Half the time, the minimum occurs during the day and you can't see it. But not only did he discover the period of algol, he also proposed a mechanism. In other words, he also tried to explain why it's happening. An eclipsing binary. I'm going to show you what that is, but first I want to show you what the light curve looks like. This is a light curve. Up here is the brightness. The smaller the number, the brighter the star. I apologize, I didn't make this up. That's how it goes. So as the numbers get bigger, the star gets fainter. And you see it's got a pretty steady brightness. All of a sudden, clunk, drops by about a factor of 3. And all of a sudden, clunk, drops by a factor of 3. Okay, very strange. And here is Goodricke's mechanism, which actually turns out to be the best. You've got 2 stars, one bright, one dim. And now the dim one eclipses the bright one. And now the bright one passes in front of the dim one. So what we see is this moment that's coming up right now when the bright one is dipping, is blocked. But the question is, do we see the second event? Can we see when the dim star is eclipsed? Well, not by eye, but if you have better data, this one shows both here's the normal dark drop, and this little blip, in fact, they found the other eclipse, which has to happen, right? If it's an eclipsing binary, these both have to be there. Can you see algol by eye? Well, of course you can, because the ancients did. And what's cool is you can compare the brightness to nearby stars, and I'm going to do that for you right now. This star here, Gamma Andromedae, this is the last star in that arc in Andromeda, from Pegasus to Andromeda, to get you to Perseus. It's a second magnitude star, 2.1 in fact. This star here is 2.9, so it's much dimmer. And this one here, Kappa, is 3.8, almost a 4th magnitude star. So when algol is at its brightest, it's almost as bright as this, and then it will dip through this star and get down to almost as dim as that. So you have these 3 stars just to gauge it. So you're going to ask them, sure, when is the next minimum? Right now, 7:30, December 8th is the minimum of algol. So if I don't talk for too long, and if it's clear outside, which it probably isn't since I'm saying this, just go outside and see if you can find this pattern. And it might be hard if you're looking for it when it's dim. It's easier to get used to where it's supposed to be and then see when it's brighter. But hey, I don't make up the schedule. I just thought it was neat. Here are the next 16 minima of algol. And if you want this information, I can, at the end, I've got my email address up there. Just send me a note and I will send these out to you. The dark green arrows are the best times, like tonight at 7:30 or at 9 p.m. On the 28th. The dim green ones are when it's not so good, like 5 or 2 in the morning. And the ones that I don't have highlighted occur during the day or too close to dusk to be easily seen. So we've talked about Perseus. Now let's talk about his neighbor Cassiopeia. This is one of the smaller constellations. It's got a fairly large area, but the W, this bright W, is small. And that makes it pretty easy to see. This is a landmark constellation, those stars being kind of close to each other. Make it, you actually use Cassiopeia to help you find other things. In the year, so I'm doing this chronologically. We started out with Algol, which is ancient. In 1572, though, something happened in Cassiopeia. A new star appeared. Now, new stars were periodically seen, maybe one every 100 years. Europe stank at this, but China had really good records. They called them guest stars. Bottom line is people didn't know what they were. And the person who's going to tell them is a man named Tycho Brahe, probably the last major astronomer before telescopes were invented, probably the greatest of them all. Greatest in precision of measurement and accuracy, and just in terms of the sheer amount of work he did. Now, this star of 1572, Brahe didn't discover it, but he was the most accurate observer of it. It appeared in November, and by mid-November, it was as bright as Venus. Nobody could miss it, okay, if you looked up in the sky. And it remained visible for not quite a year and a half before it faded beyond visible eye, before naked eyes could see it. Here is Brahe's own drawing of the star, and you can see the shape of Cassiopeia. Okay, right here, here's the W, all right. He repeatedly measured the position, and here's the, I've got, this is actually blocked. It's up here somewhere, but it's blocked by the, by my own image, so I can't see it in mine. But the position of this never changed, and the parallax was never measurable. Parallax is a way to try to measure the distance of the star. So that it position against the stars never changed showed it must be in the sky and not on the earth. It's got to be part of the stars. It really is a star. Whatever a star is, it's in the heavens. And two, since we can't measure its distance, it must be as far away as the other stars. So this violated the theory of the permanence of the heavens to have a new star appear. And his book, shortened to De Nova Stella, or The New Star, never before seen in the life and memory of anyone, that's the title, published in 1573. And it's from the title of this book and a similar title by Kepler, who also saw nova, that our term nova is derived. It's Nova Stella or new star. We just call them a nova. Where was the nova? Well, using that drawing, we can actually see where it is. Here you can see again the W. And this star right here is Kappa. So this nova right here had to be, there's Kappa, and the nova had to be pretty much in that box. Now, nothing has been seen there visibly by the eye for 450 years, but we have telescopes now. Can we see anything there? Well, let's take a closer look at that exact box, okay? This is that box. This is an image from NASA's WISE satellite, which at MSU St. Andrews, we actually used that same satellite data for research during the summer. And this is SN 1572, supernova 1572. It is this remnant here, is the remnant from Tycho Brahe's exploded star. So that's the size of it. And now, Brahe saw a nova, 1572. Any other naked eye novas to appear? Johannes Kepler saw one and recorded in 1604. And there have been none seen since then, over 400 years, and not a single naked eye nova in our galaxy. That's pretty impressive. So back to this. Here are the two pointer stars. And I'm now going to talk about Cetus and Mira. Cetus is a large constellation, all right? 6% of the area of the whole sky. This isn't as good as Pegasus, but it's certainly better than that vague W that is supposed to somehow be a queen. We've got a head, we have a long neck, and a body. This could be the Loch Ness Monster right here. It's low in the sky, though, and faint. Only these 2 second magnitude stars, but fortunately, they're both easily findable by the pointers that I showed you in the Great Square of Pegasus. So what's so special about Cetus? Mira. And that's this star right here. David Fabricius was a minister in Friesland. And in 1596, he was making observations of a planet, and he used a 3rd magnitude star as a reference for brightness. But that 3rd magnitude star wasn't on any charts, so he kept an eye on it. And in a few weeks, it doubled in brightness and was now a 2nd magnitude star. He had found a nova. Brahe had reported one in 1573. Now it's 1596, another nova. Star was gone by October. But there was a problem because the star reappeared in 1609. This was a totally new kind of thing. What was going on? A man named Johannes Holvarda, who was also a Frisian. Frisian is a northern part of Holland and Germany, by the way, right on the coast. 40 years later, after the initial observations, he studied records of Fabricius's nova, as it was called, and he discovered that a star regularly appeared there and then disappeared and then reappeared every 330 days. This is the first long-term periodic variable ever discovered. And it was named by neither of these gentlemen, but by Hevelius, who made star atlases in 1662. It was named Mira the Wonderful Star, same as miraculous, okay? Because no other star was known to behave like this. And since then, several historical novas, guest stars into Chinese literature, have been actually shown to be long-term myriad variables, which were only seen once or twice. So the light curve for Mira from this is AVSO, American Association of Variable Star Observers. This is their data. This is what they do. This is an amateur association. You can get involved with them if you wish. Period of 332 days. Look at this. Brighter than 3rd magnitude, below 9th magnitude, a range of 250 in brightness. And note that anything under about 6 magnitude, we can't see. So, and if you're living in the city, basically anything under here you can't see. So most of the time the star is gone. The star itself is a red giant. I don't really have time to get into red giants or novas or anything like that, but 250 light years away. Here's a nice image from Hubble, the Hubble Space Telescope, about 20 years ago. And it shows that the star is not even round. The key point with Mira is that it's the star itself that is changing in brightness and in color, I might add. It's not being eclipsed by something. The star itself is pulsing. And what is really cool is that no new Mira variables have been discovered for over 100 years. And don't think people haven't been looking. Can we see Mira today, meaning tonight? Yes, I saw Mira, just for the purpose of this talk, I saw Mira last week, okay? But it's about 5th magnitude, maybe a little bit brighter. Fortunately, in this area, there are no other bright stars. If you come down here, if you're looking for Mira, you better be able to see Pisces, which is faint. And you just come down here, boom, 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 there it is. Or you could take Menkar, Delta, boom, 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 there it is. It's best seen with binoculars. It'll make it brighter. The last maximum was in October of this year. So the next maximum, 11 months away, in September of 2021. So if you want to see it, get out there soon. Otherwise, wait for 9 months. So the legend of the Gorgon, Cassiopeia, and Cetus, and the stars associated. This is break time. Have there any questions been building up?
I've seen a couple of questions asking about what scale you're using for magnitude and the brightness of star.
Yeah, so
different scales.
I can go over that again. So the magnitude scale it's a logarithmic one. It's based on Hipparchus's from the 2nd century BC, a Greek astronomer. He simply took the 20 brightest stars that he could see and called them of first greatness or first magnitude. Then he took the ones that were less bright and he called them second magnitude. The ones brighter, less bright than that, third magnitude, all the way down to 6, which is the faintest he or anyone else for that matter can see. So the 20 brightest stars, 22 brightest stars are first magnitude. The next 80 are second magnitude, and then there's several hundred, many hundred third magnitude stars, etc. Between, let's say, third and fourth magnitude is a drop in actual brightness if you're measuring it using measuring instruments of about 2.5. So a third magnitude star is 2.5 times brighter than a fourth. A fourth is about 2.5 times brighter than the fifth. And if a star is partway between third and fourth, you might say it's 3.3. So 3.3 is less bright than third magnitude, for example.
Okay, this person asks, what is a Cepheid variable?
A Cepheid variable is something I'm going to talk about in the next portion of the talk, and I'll describe it.
Okay, what causes Mira to pulse? How does that change the brightness and color?
I will probably want to do another talk on stars where I can talk about variables. In these large stars in the instability strip, and actually in Mira, Mira is a type of giant. It's on the asymptotic giant branch, and it's pulsing. The pulsing of all stars have a few things in common, but the pulsing I think of Mira in particular is difficult to model. I don't want to say we don't really know, but we know that what's going on is the star is expanding and contracting somewhat irregularly, and because of the nuclear reactions that are going on inside, they will flare up regularly, and as they flare up and expand, they become less concentrated, if you will, and so they don't react as fast. This is really oversimplifying it, okay? So then they actually cool down. And so the light, by the time it comes out of the star, which takes a long time, the energy coming out of the star's shell will expand and it will actually cool. And so it will be larger and cooler, and then it will be smaller and brighter. And it's a mess, to be perfectly honest. But this brightness variation here, properly you have to refer to the color, because if you look at these stars in the infrared or in the ultraviolet, they have the same period, but they have different brightness variations because of the temperature changes. So that's a long way of saying that I don't know exactly well enough to be able to explain it well enough at a really basic level. The math is beyond me.
Okay, I guess a sort of related question. How do you know when Mira is coming again?
Well, because you have this data. You know that it peaked in what looks like maybe um, February of 2012 or 20. What is this? This is, you can just go back and forth and count from here to here to here, and it's going to be about 332 days each time. And so you simply look at the last time it was bright, and it varies by a day or two, not by 20 days, but it varies by a few days each time. But you can just go from there, and when you see the brightness and see it coming down, then you've got a peak. The next peak is going to be about 332 days later.
And what causes certain stars to pulse and not at all?
Well, there is a section of there is a range of a star's size, like we'll call it on the main sequence, where for the most part a star can be relatively steady, like our star. It's if you're a real solar scientist, you will know that our star pulses a little bit too. But Many stars are steady like our sun, but there are parts of the main sequence where the balance of gravity trying to crush the star and the forces pushing out can kind of, I don't want to make it this simple, but I'm going to kind of make a resonance. And where it pushes out, it's kind of like pushing somebody on a swing. If you just keep pushing at a certain interval, if you're pushing at the right interval, the swing goes bigger and bigger and bigger. It's the same sort of thing, except in 3 dimensions with a star. And there's an entire area of the brightness curve that stars are unstable for various reasons. And there are our Lyrae stars, and there are all kinds of variable stars, and they're all in the so-called instability strip, where in that region, the harmonics of the stars, I guess, cause them to beat like a drum. And it's natural.
Okay. How about one last question, then we can move on. Okay, so why did the nova dim and disappear?
I'm presuming they're talking about Kepler's, or sorry, Kepler's and
Brahe.
Tycho's nova.
Yep.
Yeah, and that is the normal thing for a nova. For Tycho's nova, that was, I guess I can't answer this without getting into stuff, but Tycho's nova was a type 1a nova. And what that means is that it was a white dwarf star, which is very hot and extremely dense and small. And it's slowly pulling mass from a companion star, and the mass is piling up. And the white dwarf has stopped hydrogen fusion for the most part. But as this new material comes into this very hot star and accumulates, all of a sudden hydrogen fusion kicks on again. And when it kicks on, there's now all kinds of fuel. And it's a thermonuclear runaway. It's not like a normal star where the gravitational pressure keeps the star in, and the radiation pressure from the nuclear explosions keeps it out. This is something that was stable until it kind of hit a point, and then the whole star flares up and releases a tremendous amount of energy until all that hydrogen is burnt off, and then it slowly is burning off. Then it slowly dies down again until it goes back to being a white dwarf again. And if it hasn't destroyed the companion in that process, that type of supernova can repeat again as the pulling of mass from its companion star continues. Okay, so we said continue at this point. So someone asked about Cepheid variables. The next star is Cepheus. Again, an average constellation. It's bigger than Cassiopeia in terms of its little house-shaped thing. Again, why this little thing which looks like a house or maybe a dunce cap, how this is a person, a king, I don't know. But it's dim. This one star here, Alderamin, is second magnitude, barely. The rest are third or fourth magnitude. What's special here? Delta Cephei, Cepheid variables, this star right here, which again, I'm choosing these carefully. You can see this with your own eye. Excuse me. Remember John Goodricke? Yes, the discoverer of Mira's periodicity, or periodicity. He also discovered Delta Cephei and others. This is a lot for someone who died of pneumonia at age 21. By this time, not quite a dozen variables were known. And so what's special about Delta Cephei? Frankly, how easy it is to observe. This is the light curve of Delta Cephei. Now look at this. For one thing, it's a 5-day period, okay? So you can basically determine it in a few weeks, okay? The magnitude range, 3.5 at the high end to about not quite 4.5 at the low end. So you can observe the high and the low just easily. So, and it's also a smooth curve. So it's a steady rise and fall. There's no like long periods where the star is invisible like Mira and you don't know what's going on. There's no sudden spiky dips like Algol was, so that if you get clouds for 3 hours, you've missed it. Okay. Very easy to see. So does this light curve have any use? This light curve is critical to our understanding of the universe. And I will come to that when we get to our next constellations. Can you see this for yourself? Yes, as I've already said. And it's even better than that. This is all set up for you to enjoy because there are convenient reference stars to judge the brightness with. So here is, you can see the red circles down in this area. Here in red is Delta Cephei itself. Its nearest neighbor and brightest neighbor, Zeta Cephei, is about magnitude 3.6. And its other near neighbor in this cute little triangle, Epsilon Cephei, is 4.2. So here's this little triangle. At its peak, Delta Cephei is just barely brighter than this neighbor. At its trough, it's just barely dimmer than this neighbor. So you can just look at this triangle and Cepheus, assuming you can, if you can find Cepheus, you can find these. And if you find these, you can just look at the three of them and you will know where Delta Cephei is in terms of brightness because you've got these two stars right next to it to compare it with. So you can do this yourself. Here I've got a slide that I wasn't going to talk about, but I had a feeling people were going to ask. So here's this instability strip that I was talking about. And here is Mira over here in this curve. So these regularly pulsating stars are keys to the way we understand the universe. And that's what I'll be talking about soon. Because what use is this? Well, the problem with stars is what we saw in the, remember when I spun the Big Dipper around? Some of those stars were really near, some were far away. Well, when you're looking at a star and it's, you know, a third magnitude star, is that because it's a faint star, but it's really close, so it looks bright? Or is it a tremendously bright star, but it's very far away? And it would look the same. You can't tell. But what Henrietta Swan Leavitt did was she was working with Pickering at Harvard. And in 1908, she was studying variables in the Magellanic Clouds. These are small groups of stars in the southern hemisphere. Though, sorry, we can't see these from Midland. She studied over 1,700 variables. But the key was, since they were in the clouds, which were very far, which were believed to be far away, they're all the same distance. So even though we don't know how bright the stars truly are, when you see two stars in that cloud and one's brighter than the other, you know one is brighter than the other. You don't know the absolute brightness, but you know the relative brightness of all of them. So she found Cepheid variables in the clouds and other variables as well. And she measured their periods, the maximum and minimum brightness. And she measured the repetition. And she published a key paper in 1912 on 25 variables. And here is her data. She found that she plotted each one of these is a pair of stars, okay? Here's a pair. This is a pair, okay? This right here, that's a pair. The brightness, the brightest and the dimmest, remember, the bigger the number, the lower the brightness. And what she found is that there are two lines. There's a line going through the dim part, there's a line going through the bright part. And it's plotted against period, the number of days it takes to go from bright to bright or from dim to dim. So the brightness depends on the period. That means that if we measure the period, we will know the relative brightness. All we need to do to know the absolute brightness is to measure the distance to some of these stars. So Hertzsprung and Shapley were working on this in the teens before the war, and before the First World War, and they determined the distance to some of these. So now we had a yardstick. If we find a Cepheid variable anywhere and recognize it as a Cepheid variable, that's not trivial to prove that it's this particular type of variable. And we measure its period, we will know its true brightness. And then by looking at how bright it appears, we will be able to calculate its distance. So these are the yardsticks of the universe. So that is my answer to the question on Cepheid variables. So that's what makes Cepheus important. Here's the constellation of Andromeda. This is also very easy to find because, for one thing, it's right overhead right now, so it's not hidden by trees. Here's the Great Square of Pegasus, and you may remember those four stars here going on up. All right, and there's a second line of stars here and here and here, which kind of like the two legs of Andromeda. She's got an arm sticking out this way, an arm sticking out this way, and hands. I mean, she's chained to a rock, so she's got her arms spread out. But what's special about Andromeda? A fuzzy patch of light, again, that you can see with your unaided eye, maybe not right in the middle of downtown Midland, but where I live, I can see it. I'm 4 miles out of town. And that's this thing right here, which we're going to call M31. It's a designation from an astronomer several hundred years ago. How long has this been known? Well, I don't know. But the first mention that I'm aware of is Abd al-Rahman al-Sufi, the great Arabic astronomer. Yesterday was the anniversary of his birth, and in 2016, I was delighted to find a Google Doodle for him. He's known in the West as Azofi. You get to see al-Sufi, Azofi, Azofi the Arab. He translated Ptolemy's works, and he corrected much of it. And in 964, he published a book of fixed stars, and he clearly describes this little cloud in Andromeda. So at least he saw it. Can we really see it? Absolutely. And I'll help you find it. Now, you remember this from Pegasus, Alpheratz, Merak, Almach, and Mirfak, those up here in Perseus, those 4 second magnitude stars. Just go at an angle from these, and you'll see this star, and then you'll see a faint fuzzy patch visible to the eye in decent skies. Another way of doing this may be better if you're in the Midland areas with binoculars. What you'll see, and I'll go back again, you see this little thing I'm bringing in here, this little yellow thing moving across. That's about the size of what you'd see. It's about the size of a little bit smaller than the full moon. But if you get binoculars, you can find Merak, and you can get Merak and Mu in the field of view at the same time, and then Nu, and then you can just move slowly along and you'll find M31 and you'll get a nice view of it. In an amateur telescope, you'll see a bright core and an extended region. And a better telescope like this one, or well, a good photo, you can see that there's dark lanes. There's a kind of a spiral structure, this like a spiral seen at an angle. And this is another image of M31, different flipping of it. And you can really see the spiral structure into dust lanes in this one. And the cover image to this talk was also M31. But telescopes have seen other spiral clouds like this. So what are these? Here's one. This is the Whirlpool Nebula, which is in Ursa Major, you can see it. These were always assumed to be gas clouds, maybe even solar systems in formation, located somewhere within the Milky Way, something like 10,000 light years in our galaxy. But in the 1860s, Sir William Huggins analyzed this by spectroscopy, breaking light into its components and analyzing it. And these spiral nebula, by the way, is simple. Everything's done in Latin in the old days. It's the Latin word for cloud. So these nebulae, these clouds, did not look like other gas clouds. They looked more like stars by spectroscopy. And furthermore, novae also seem to occur every now and then in some of these nebulas. So that argues for it being further away. And there is actually something called the Great Debate. It happened in the 1920s about these spiral clouds, spiral nebulae. Are they nearby gas clouds, or are they stars at an unimaginable distance? Enter Edwin Hummel. This is, okay, I'm going to have to, I can't see, there we go. Right here, this is his actual plate of the Andromeda Nebula, and I'm circling 2 lines that he's drawn on the glass plate, and there's a star that I'm covering up right now that he discovered was a Cepheid variable in the Andromeda Nebula. So Henrietta Leavitt's data on Cepheid variables were going to settle this question. It turns out that Cepheids, I'll do two examples here. Cepheids, Harlow Shapley looked at clusters of stars around the galaxy, told us that the Milky Way was not a few 100 light years or 1,000 light years, but 100,000 light years across. This was determined with the Cepheid variables. This was almost unimaginable to astronomers at the time. It was a tremendous controversy. And Hubble, looking at that Cepheid in the Andromeda Nebula, we now know it as the Andromeda Galaxy. It is over 2 million light years away. It broke the universe wide open, distances we can't even imagine. And all because of the variable stars. And now finally, Pegasus. Pegasus is, I saved the best constellation in a way for last, very bright, very large. If you add its legs, which is the constellation of Andromeda, it becomes the largest constellation in the sky. What's also neat is this great square of Pegasus has one more feature. And use this. It gives you a dark sky test. If you look at this, and you'll have to let your eyes get used to the darkness. This takes 15, 20 minutes. Don't go out from the house and look up and try to see it. Spend 20 minutes out there before you look. If you don't see any stars in here, your skies stink. If you see one star, that would be this one. It would be a 4th magnitude star. If you see 4 or 5, you're seeing maybe 4th or 5th magnitude. You're seeing these stars with the names on it, and this one here. If you see 10 or more, you have a dark sky. So one more thing with that great square. What is special in Pegasus? How about a Nobel Prize in physics? And it's because of this star right here. Yes, another star. I'm circling it. You can see it with the unaided eye, but it's faint. 5.5, you're going to have to be in a dark sky. So what is this about? I'm titling the slide "A World Beyond Our Own." People are always wondering about life beyond Earth, okay? Now, nobody's discovered life in other worlds, okay? But people have always wondered what it would look like. What would it need? Liquid water? Would it need an atmosphere? Is there a certain type of star it needs? But one unstated assumption that everyone accepts is that you need to be on a planet. This isn't going to be in a gas cloud. So the only problem with that is for 4 centuries after the invention of the telescope, not a single planet was ever discovered. So, oh, incidentally, I don't know if any of you recognize these, but this is actually something that used to live on Earth, the Tully monstrum. But it's weird enough that I thought I would use this as extraterrestrial. But the first exoplanets. Some evidence in 1988, disputed for a while. 1992, 2 planets were found orbiting a pulsar. Well, for life, that's certainly a disaster. But in 1995, 2 astronomers found a planet orbiting that star that I circled, 51 Pegasi. They used a radial velocity method. They're measuring the star vibrating back and forth as it's being pulled by this planet, a heavy planet that's orbiting around it. The star is a lot like our sun, little larger, little heavier, little older, and about 50 light years away. The planet is about half the mass of Jupiter, so it's fairly large, but it's only, it's like 1/8 the distance of Mercury from the sun. It is really close to its star. It's so close that instead of 365 days like Earth, or 88 days like Mercury to go around its star, it does it in a little over 4 days. Estimated temperature of 1800 degrees Fahrenheit. This is where the term hot Jupiter came from this star. And exoplanets are another topic for a future astronomy night. There is so much there, especially lately. But I just want to say that in 1995, last year, the Nobel Prize was awarded to some astronomers. And 2 of them, Michel Mayor and Didier Queloz, were for the discovery of an exoplanet orbiting a solar type star. So I am now done with um, the constellation part. The technology update is a sad one. I'm going to talk a little bit about radio astronomy. Radio astronomy doesn't use telescopes. It doesn't use glass. It uses very large arrays, big reflective surfaces, just like a reflector, but they use metal grids, so they can be really large. This is the Jodrell Bank. It was the largest in the world at one time. It's 250 feet across. But this whole thing, as you can tell by this arc and this arc here, this whole thing has to be steered in two independent directions. What if we could find a large valley that already had the correct bowl shape? Well, there is such a thing, and this is the Arecibo telescope. This is the scope itself down here. There's a natural sinkhole. They covered it up with metal. It's 1,000 feet across, the largest telescope in the world. Up here are the instruments that are being hung by cables from 3 towers, both receivers and transmitters. And the cables move the instruments. Instead of moving the dish stays put. And as the Earth turns, they move the instruments to stay in focus. Really clever system. What does it do? A lot of things. A lot of things. The only one I'm going to talk about is planetary defense. Other telescopes are better set up for discovering near-Earth asteroids, which are important because they could hit us and cause real problems. So once they're discovered, you need to use radar to estimate the size, shape, and the orbit. So you need a powerful transmitter as well as a sensitive receiver. There's 2 in the world that do this well enough. One is Goldstone, which is part of the Deep Space Network, which controls our various, that's where we get our information going to Mars, and the Cassini probes and the Voyager probes way out in interstellar space. Arecibo was the best in the world, and it was 20 times more sensitive than Goldstone. And I chose Arecibo because 2 weeks ago, they found problems with the cables. There's been too many. Was built in the 60s, and it is started in the 50s. So it was like, it's 60, 70 years old, too much weather, too many hurricanes. Cables were starting to get a little frayed and a little corroded. And NASA was thinking that they would have to decommission this because it would be very difficult to repair. But last week, the decision was made for us. Some brief updates because there's so much going on. There's samples coming from everywhere. China's Chang'e 5 mission is bringing samples back from the moon. Japan's Hayabusa 2 is bringing asteroid dust from Ryugu. And NASA's OSIRIS-REx, which we talked about last month, is bringing stuff back from Bennu, but that's going to be well before it gets to. But these other 2 are coming back now. So at this point, I think I am done. And are there any questions? My address here, starked@msu.edu, if you want some of the information that I gave as suggestion for observing. And let's see what people have asked. Thank you very much and good night.